Shall we start? Shall we start, Reno? Chemical bonding. We have like 9 more lectures for chemical bonding. That's crazy. It's the most important. The first 2 chapters, like I say, are the most important 2 chapters of your A levels. After the first 2 chapters, every chapter is 5 lectures, 4 lectures, instead of except for organic chemistry. Organic chemistry is half of your syllabus. So you'll be done with 50 to 60% of your syllabus very, very soon, inshallah, within the next 2 to 3 months. And then we will solely focus on organic chemistry, because that's 50% or 40 to 50% of your entire course. And it's also 40 to 50% of your examinable course. So that comes in your exams. But these topics right here, the ones that you are studying right now, electronic configuration ho gaya, this chemical bonding ho gaya, these topics are going to build your basics for organic chemistry. You can never understand organic chemistry if your physical chemistry and inorganic chemistry is weak. Never, ever, ever. Yeah. Fatma is saying, I have marks in November. Fatma, it's okay. Just we'll skip on those marks, right? Because we really don't care. We care about the final result. We care about unless you're applying to the US. If you're applying to the US, then you'll also have to, make arrangements with your teacher to give you good grades in your marks, so that when your transcript goes on the Common App, you're not put at a disadvantage, because the mock grades, and it's not just the mock grades. If you're applying to the US, all your grades from grade 9 till grade 11 will be submitted on your Common App. So those who are not in a very in a very regulated school, you guys can just even ask your teachers to give you A's and A stars in your papers. That's how it happens in our country. Chalo, moving on. We started. Why have I written 9-11? That's crazy. I meant grade 9 to grade 11. Okay. Now, today what we are going to do is, we learned the idea of pi bond, we learned the idea of sigma bond. We know that sigma bond is way stronger than pi bond, and pi bond is basically the sideways overlap or the parallel overlap or the lateral overlap of the orbitals. And which orbitals? Well, that's just the p and p orbital. But sigma can form between the s and p, the SNS, and even the p and p. It can also form between the overlap of the p and p orbital. But what's the difference between these two overlaps? Well, one is a sideways overlap and one is a head-on overlap. That's the difference. And if I ask you if chlorine, because we know chlorine is in the p block, right? So it will have the p orbital interacting when it's making the covalent bond. Now, if chlorine were to make a bond with another chlorine atom, both their p orbitals will be involved, right? It'll be a p and p overlap. And we all agree to that. We've all studied that. It's going to be a p and p overlap. Now, my question to you guys is, will it be a sigma overlap? Would it be a sigma bond or a pi bond? Would this p and p overlap, the first p and p overlap, result in a sigma bond or a pi bond? We know that the sigma bond is always going to be formed first, because the first overlap is always head on. The reason why the other overlaps are not head on is because, practically speaking, you can't have 2 head-on overlaps in a particular orbital overlap. What you can have is a head-on overlap, and after the head-on overlap, that restricts further head-on overlaps. So what happens? Well, then sideways overlaps happen, and then that results in pi bonds, like in oxygen double bonded to oxygen. The first bond is my beautiful sigma bond, and the second bond is the overlap of pp orbitals. But remember, that's the sideways overlap. So my drawing is pathetic, but you get the idea. I've shown you a lot of pictures even. And if I draw this in the exam for the orbital overlap, I'll get 0 marks, because both the orbitals are not of the same size. But we know that in a particular subshell, if we talk about the p subshell, all the 3 orbitals in a p subshell are going to be of the same size. But if you increase the principal quantum number, so if it's the 2p, all the 2p orbitals will be of the same sign. But if it's the 3p, all the 3p orbitals in the 3p subshell are going to be of the same size. But the difference between 2p and 3p is first the energy and the size. The 3p lobes are going to be larger, and the 3p is at a higher energy level. We've studied that in chapter number 1. Just giving you guys a recap. Yeah. Now, we learned all of that good stuff, and we also understood the idea of Lewis dot and cross diagram. So this is just a visualization of orbital overlap. It's a visualization of orbital overlap. But if they were to ask you to show me the sigma and the pi bond, what do? Well, the sigma bond is shown by just the stick, and the pi bond, you're just gonna draw, these two bean-like, kidney bean-like structures. Although I am drawing it like this, and even in the exam it's going to be drawn like this, but in reality they look more like a kidney bean. Now my drawing is pathetic, but in reality it looks something like this. But hey, who cares? Even the exam does not. It's something like this. Like this, yeah. Oh, I've got the hang of it. Sir Suleiman's drawing is now, in reality it looks something like this, yeah. And the pi bond is weaker compared to the sigma bond, but a triple bond or a double bond is stronger than a single bond. Why? You might say, sir, this has a sigma bond and it has a pi bond. Isn't the pi bond weaker? It is weaker, but the double bond, the strength of the double bond is a combination of sigma and pi. This is just a sigma bond. So realize that the double bond is always going to be stronger than the single bond, and the triple bond is way stronger than the double bond and the single bond. And why? Because it has a sigma and two pi's, and this just has a sigma and a pi. So there are more bond interactions in a triple bond compared to a double bond and a single bond, right? So the more bond interactions there are, the more sigmas and pi's you have, the stronger the bond is going to be, because that results in stronger electrostatic force of attraction, right? And then when we were starting off with this chapter, we learned something known as the Lewis dot and cross diagram, which we also studied in O levels and IGCSE. And we understood the fact, I drew a diagram for you. I drew a Lewis dot and cross diagram for a particular molecule. If you remember, I drew a diagram for this particular fella right here. I said that, you can have dot and cross diagrams. You can have chemical bonding without the octet rule being satisfied, without the duplet rule being satisfied. You can have chemical bonding without, sir, I love the previous lesson recaps. They help in long-term memory so much. I'm glad, Fatma. Thank you. That's lovely. That's the reason why we do recaps, because it's called spaced repetition, Fatma. So I focus on spaced repetition, spaced, right? So in the last classes, we also learned the Lewis dot and cross diagram for this fella right here. And the reason why I taught you guys this was in order to, clarify the concept or clarify the misconception that always, if there's chemical bonding, it will always satisfy octet rule. It will always satisfy duplet rule. It will always satisfy complete outermost electron shell, right? But we realize as we move on and on and on with our chemistry, that's true, but only to some extent. There are exceptions. The octet rule, see, it also says octet rule. It's just a rule of thumb. Complete outermost electron shell, it's just a rule of thumb. In reality, these chemical bonds, actually, why do elements undergo chemical bonding? Till O levels, we said in order to have a stable electronic configuration and, in order to have a complete outermost electron shell. But now we realize that they do have stability. Some fellas, they do have stability. They are stable, but they don't have a complete outermost electron shell, but they're still stable. Now, why would they undergo chemical bonding? Why would elements undergo chemical bonding if they're not completing the octet rule, if they're not following the octet rule, if they're not following the complete outermost electron shell? Because that's just a rule. The reason why they undergo chemical bonding is because bond formation is a favorable process. And you learn more about that in A2 level chemistry. But bond formation is a favorable process. As long as you can form bonds, they will undergo chemical bonding. Yeah, as long as these atoms can form bonds, they will undergo chemical bonding, because bond formation, you've studied this in O levels and IGCSE, is exothermic. It gives out heat energy. It gives out energy. And if energy is given out, that means your overall energy is being minimized. The molecule's overall energy is being lowered. And if your energy is overall being lowered, you are becoming more and more stable, right? So stability in reality, if you look at it, from the core concept, it all has to do with energies. It has to do with bond formations, because bond formation is favorable, 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 and octet rule is just a rule of thumb which helps us draw a lot of molecules which we've learned in O levels and IGCSE, and we will still use the octet rule. We will still use the octet rule in A levels for molecules we've never seen before, but realize that there are exceptions to the octet rule, because the octet rule is just a rule. The reality is bond formation. The reality is bond formation is favorable process, and molecule and atoms are gonna undergo chemical bonding. They will make bonds even if they don't satisfy the octet rule in order to lower their energies, in order to lower their energy. And fun fact, even noble gases can undergo chemical bonding, but that we don't study in A levels, so we are gonna say noble gases don't undergo chemical bonding. They are inert because they have a stable electronic configuration. We'll use the same wordings of O levels and IGCSE. Yeah. Now, if you look at this fella, I know carbon is in group 4. It has 4 electrons in its outermost shell. Group 4, 4 electrons in its outermost shell. Group 6, it has 6 electrons in its outermost shell. Now, if you have to draw this Lewis dot and cross diagrams, I'll use the same circles that we used to use in O levels and IGCSE, although it's not important to use the circles, but the reason why I'm using it because you guys are more familiar with it. Now see, this is carbon double bonded to the oxygen, and each bond represents a pair of electrons. So that's a pair of electron and a pair of electron. Good stuff. And similarly here, that's a pair of electron and a pair of electron. Now you guys can say, sir, oh my god, this is carbon, this is carbon. Shouldn't all these 4 be crosses? It's up to you. If you want to make all of these 4 crosses, it's up to you. The reason why I'm showing 1 dot and 1 cross is just to differentiate that this electron came from this fella, this electron came from this fella right here. That's why. So both are correct. Both are correct. You can make 4 crosses if you say that, hey, they are both carbon, so they should be represented with crosses. You can make 4 crosses here and the examiner would not mind it, right? So it's both of them are acceptable. Now, that's my bonding electron. So it's 4 plus 4, 8 bonding electrons. What about the electrons in the shell, the electrons which are not involved in bonding, right? The lone pair electrons. Well, if this was in group 4, this carbon contributed 1 electron here and 1 electron here. So 2 are left, you know. I can draw it inside as well. I can draw it on top of this shell as well. It doesn't really matter, you know. And then oxygen was in group 6. This carbon was in group 4. It gave 1 electron to this bond, 1 to this bond, 1 to this bond, 1 to this bond. So all of its 4 electrons are utilized. Good stuff. And if you look at oxygen, it was in group 6. It gave 1 electron here, 1 here. So 4 are left, aka 2 lone pair electrons. I can draw it with crosses. I can draw it with dots. It doesn't really matter, you know. Now, if you look at the lone pair, it's 1, 2, 3, 3 lone pairs. 3 lone pair electrons in this particular molecule. 1 pair, 2 pair, 3 pair, not 4. It's 1, 2, 3, 3 pair, right? Now, if you look at this fella, it does actually happen. Appreciate the fact that this does exist. This does exist. This fella right here does exist. But you'll see something strange about it. What's strange about it is that, hey, this carbon follows the octet rule. This oxygen has followed the octet rule. But this carbon right here, it has not followed the octet rule. It's 2, 3, 4, 5, 6. But it still happens. And you should know that it can happen. That's the possibility that you need to understand, that this possibility is in fact true, because the reality behind bonding has to do with bond formation. So maybe this carbon was not able to satisfy its octet, but the reason why it still underwent chemical bonding is obviously because bond formation is a favorable process. It would give out heat energy and therefore would make it stable. That's why it underwent chemical bonding. But let's stick to our O-level IGCSE chemical bonding, in which these octet rules are not, defied. Let's just talk about the molecules like PCl3. Let's talk about CH4 molecule. Let's talk about HCl molecule and whatnot and whatnot. Now, I want you guys to make the Lewis dot and cross diagrams for these like you used to in O-levels and IGCSE. How would you do it? Well, phosphorus is in group 5. It's gonna need 3 electrons, therefore it makes 3 bonds, following the octet rule. And now the question is, how do we know when to use the octet rule and when not to use the octet rule? Well, you just need to know certain exceptions. Other than that, keep the octet rule at the back of your brains, right? And chlorine is in group 7. It just makes a single bond. So if you were to make phosphorus being bonded to chlorine, it's phosphorus, chlorine, 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 right? And if you show the dot and cross diagrams, that's P, that's Cl, that's uno dos Cl, and that's tres Cl, as Cl, and phosphorus was in group 5. It gave one electron to this bond, one electron to this bond, one electron to this bond, and one lone pair electron is right here. Yeah, and draw the electrons of chlorine which aren't involved in bonding. So chlorine was in group 7, gave one electron here, 6 are left. So 2, 4, 6, 2, 4, 6, 2, 4, 6. I want you to do CH4 on your own and HCl on your own. Please do it. And you know, the way you make these Lewis dot and cross diagrams is to look at the central atom. Always keep the central atom. See, I'm teaching you guys thought process. How do I know that these 3 chlorine atoms are all bonded to phosphorus? Because when I saw phosphorus, I realized that it can make 3 bonds. And the central atom is usually the atom to which all the other atoms are bonded to. The central atom is usually the atom which makes the most bonds. That's the central atom. In HCl, there's really no central atom. You can't segregate it. In this case, see, what is your central atom? That's my central atom. So obviously the 4 hydrogens are gonna be, bonded to the carbon atom right here. And HCl, there isn't really a central atom, so it doesn't really matter. Yeah. It's just H bonded to Cl. It's just H bonded to Cl. So I want you guys to draw CH4 on your own. See, it's carbon is my central atom. Why? Carbon is in group 4. It needs 4 electrons to become stable, and therefore it will make 4 bonds. Hydrogen just makes 1 bond. We know that. So hydrogen, 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 hydrogen. And that's good stuff. We've learned that in O levels and IGCSE. Doom, doom, boom, boom. Everybody's happy. Everybody's happy. So usually the number of electrons that you need to become stable, so in this case, the number of electrons that you need to become stable, aka have a complete octet, is going to be, or a complete duplet in case of hydrogen, is going to be the number of bonds that you're going to make. So phosphorus was in group 5, it needed 3 electrons, therefore made 3 bonds. Carbon, group 4, needed 4 electrons to complete its rule, and therefore it's going to make 4 bonds right here. Now, there's a problem. Just like the problem I showed you right here. That's called exceptions. So there's exception to the octet rule. There's exception to the complete outermost electron shell. And that's called defying the octet. Defying the octet rule. Sir, why was this not taught to us in O levels? Because they did not. If this was taught in O levels, probably your brains would have gone bonkers. Yeah. Now, defying the octet rule. I'm not going to just teach you exceptions. I will teach you the way to think. So, let me add the periodic table here. Let me add the periodic table. Although what I'm going to teach right now, you don't need to know it, but I will still teach it. Why? Why, you may ask? Because I am me. I can do it. I am me. I can do it. Where's the beautiful periodic table? I've annotated this for electronic configuration, but hey. Let's just, enlarge this a little. Larger, larger, larger. Okay, good stuff. Now, defying the octet rule. Which elements or which atoms would normally defy the octet rule? Let's look at the first period which actually defies the octet rule. And the elements which defy the octet rule are found in period 2 and period 3. We're just going to look at period 2 for now. We're just going to look at period 2 and why it's period 2. You don't need to know why it's period 2. But I'll tell you, in period 2, you have beryllium. When it makes like a covalent bond, it's going to probably defy the octet rule. You have boron, which will defy the octet. You've seen carbon defy the octet rule. You can also have, in period 3, you can have aluminum defying the octet rule, and so on and so forth, right? So you can have these beautiful fellas. You have phosphorus defying the octet rule. You have sulfur defying the octet rule. And that just happens. Just appreciate the fact that it happens. But you may wonder to yourself, sir, if these are the only elements, there must be a reason to it. There must be a reason to it. You might wonder to yourself, and there is a reason to it, and I'll tell you in a while. But for now, I just want you to understand the exceptions. The exceptions are like, boron being bonded to 3 fluorine atoms. Then you have, like beryllium being bonded to 2 chlorine atoms. Then you have aluminum being bonded to 3 chlorine atoms. Then you have C double bonded to C double bonded to O. These are my exceptions, and you need to know these exceptions by heart. But I'll teach you the reality behind it, the actual core concept behind it, and then you won't need to remember it. You just know it for the sake of understanding it. Now, oh sir, what are you saying? AlCl3? Isn't AlCN3 an ionic compound? Isn't AlCl3 an ionic compound? Yes sir. Isn't AlCl3 an ionic compound? Isn't this a metal? Isn't this a non-metal? Did we not demystify the concept of metal and non-metal? It doesn't really have to do anything with metal and non-metal. It has to do with electronegativity difference. So the electronegativity difference between aluminum and chlorine is less than 1.8. And if it's less than 1.8, we know that if it's less than 1.8, it makes a covalent bond. It makes a covalent bond. So it's not an ionic compound. It's a covalent compound, not an ionic compound. And how did scientists prove this? Because electronegativity values are all arbitrary. They're all relative values. All relative. The Pauling scale is also flawed. It's all relative values. Remember the nitrogen and chlorine flaw? But these are all relative values. Then how did we know that AlCl3 is covalent and it's not ionic? We made these electronegativity values on our own, but how in the world did we know initially that AlCl3 is not ionic, it's covalent? Any hunch, any guesses? It's pretty simple. Observation, experiments. We saw that AlCl3 did not have the properties of an ionic compound. We saw that it had low melting point and boiling point. It had low MP and BP. Ionic compounds usually have high melting points and high boiling point due to electrostatic force of attraction, strong electrostatic force, but they have weak intermolecular force of attraction. It turns into gas early on heating. It does not conduct electricity in any state. If it were ionic, it should have conducted the electricity in molten or aqueous state because of mobile ions, but it doesn't conduct electricity in any state. So these were the proofs. Literally. And we know the formula of AlCl3 using moles and stoichiometry and ratios and whatnot. Not through its charges. But the question is, why? Sir, why are these the exceptions? You don't need to know the why. But I'll talk about, a couple of whys with you. Slowly and gradually we'll demystify every why. Let's talk about the why behind beryllium, and let's talk about the why behind boron. The ones which are in period 2, and they belong to group 2 and group 3. Just boron and beryllium. They are in period 2 and belong to group 2 and group 3. What you need to understand about them is, if I were to make these bonds, so let's just make BF3 and BeCl2. Can we make BF3 and BeCl2? Can we do that? Let's first write the electronic configuration of BF3, let's forget about the electronic configuration. Let's just draw the BF3 bond and the BeCl2 bond. Yeah, let's draw it. So we know boron is in group 3 or group 13, therefore in this case, it has just made 3 bonds. Although it should have followed the octet rule, but it's not. You guys can check it out here. It should have followed the octet rule, but it's not following the octet rule. It's just bonded to F. It's just bonding to 3 Fs. So if I were to draw it, you can't say it's in group 3. It needs 5 electrons to become stable. Therefore, it will make, 5 bonds and whatnot. No, you can't do that right now, because now this is the exception. So it's in group 3, but he's shown you that it's only bonded to 3 fluorine atoms, which means if I have boron atom, it's going to be bonded to 1F, 2F, 3F. The examiner has told you it's just being bonded to 3 fluorine atoms. And I'll show you why later on. I just want you guys to understand why this is the exception, right? So this is one bond. That's the other bond. That's the other one. It's like B being bonded to 3 Fs. 1, 2, 3. The examiner has showed me these 3 Fs. Good stuff. And if I were to write down the electrons which are not involved in bonding, these are 6. That's 6. And for boron, it was in group 3. Boron, it was in beautiful group 3. So it only had 3 electrons in its outermost shell. And it gave 1 here, 1 here, 1 here. What's the problem? Can you guys see the problem? Yeah. I also want you guys to draw BeCl2. So BeCl2 is just Be bonded to 2 chlorine atoms. Bonded to 2 chlorine atoms. Right here. Beautiful. So Be, I've given you the formula for it. You just need to draw it. BeCl2. So it's Be was in group 2, made 2 bonds, one here, and chlorine is 2, 4, 6. 2, 4, 6. What students tend to do is they just start to complete this as well. Like, oh, 2, 4, 6. Oh no, you dumbo, it's in group 2. Only had 2 electrons in its outermost shell. One is involved here, one is involved here. What's the problem you see with these two molecules? What's the problem? Think about it. What's the problem? The problem is that they don't have a complete octet. Boron doesn't have a complete octet. Beryllium doesn't have a complete octet. Question, why does it even undergo chemical bonding if it's not following the octet rule? Because that's just a rule. It's still going to undergo chemical bonding because bond formation is a favorable process. It's energetically favorable. So because it's energetically favorable, they're going to undergo bond formation, give out heat energy and become stable. That's why. But the question is, sir, why don't they just take, okay, if their octet is not complete, what if we can somehow complete it? What if we can, because I have to explain other elements to you guys later on. That's why I'm giving you guys this idea. What if we can somehow complete it? Can we not just give this 2 electrons? You know, that idea is possible. Why can't I just give this 2 electrons from the outside world? Why can't I just give this 4 electrons from the outside world for it to complete its octet? That's possible from the outside world. I could do that forcefully, but it wouldn't happen. It wouldn't happen on its own. Why? Because realize that boron and beryllium, now see, all the concepts are going to come into play. Boron and beryllium are not that electronegative. They're not that electronegative. So even if somehow you manage to give it electrons, it would make the molecule very negatively charged and unstable, because that's not electronegative. It's not that electronegative. It doesn't want to take these electrons. No, it's like, hey, no bueno. I'd rather be like this than this. If you give me electrons, I could somehow do that, forcefully do that, but that would make this unstable. So on its own, it's not going to do it because it's not that electronegative. See, it's towards the left of the periodic table. It's not lying towards nitrogen, oxygen, fluorine. These are pretty electronegative. Phosphorus, sulfur, these are electronegative, not boron and beryllium. So they're like, hey, we're happy. Even carbon, they're like, we're happy. This fella that I showed you here, this fella right here. So they're all happy. They're just, they're just chilling. They're just chilling. So remember, when you have period 2s, normally the ones in period 2s, they don't complete the octet. So they have fewer electrons than the octet rule. Normally, the ones which have fewer electrons than the octet, they belong to period 2. Normally they belong to period 2. Right here. So it's like boron, beryllium, carbon, they're just chilling right here. Now there's also one more idea. I want you guys to write the electronic configuration of boron and beryllium. There's also another idea. I want you guys to write the electronic configuration of boron and beryllium. Boron, and although don't write the electronic configuration though. I just want you guys to understand how many principal quantum numbers there are. So beryllium has principal quantum number 1 and 2. Yeah, it has 2 principal quantum. So has boron, so has carbon. It just has the 1 principal quantum number 1, shell 1, and it has PQN2. Yeah, just keep that in mind. Don't write the electronic configuration for now. It has PQN1 and PQN2. Why am I telling you guys this? You'll know in a while. You'll get the idea in a while. So what I want you guys to do is, I want you to make these 3 exceptions again on your own. So BF3, I want you to make the dot and cross that. And these are commonly tested in your exam. I want you to make BeCl2. I want you to make like AlCl3. And I want you to make this fella right here. These are the only ones which are going to be tested in your exam. The only ones. So I want you guys to make this. And please understand the fact that normally it's the group period 2s. Normally it's the period 2s which, period 3 is also there, but normally if you check it out, it's boron, beryllium, carbon, which have fewer electrons than the octet. And even aluminum, it belongs to period 3, but even aluminum. I'll tell you why in a while. थोड़ी देर सबर करें, इंशाल्लाह मैं आपको सब कुछ बताऊंगा. Things that you may otherwise not come across. So I want you guys to make this, and I hope everybody is making this. Fatma is saying, my life has been a joke. In A levels, when I used to teach A levels back in the day, students used to say the same. And then they used to come to the class and they used to be like, "It's a joke, man. What have we learned in O levels? It's all been a lie." It's not lies, it's just half-cooked truth. See, the octet rule is also half-cooked truth. It works. It works. Sometimes it doesn't. When it doesn't, you need to know the reality that it's just a rule. So that's the first problem with the octet, yeah? So keep this in mind. Aluminum bonded to 3 chlorines, and I hope you guys can make it. I've already made it at the top. Beryllium, always make the bonds first for yourself. So beryllium bonded to 2 chlorines right here. Boron bonded to 3 fluorines. Don't complete the electrons by saying, oh, let's complete 8 electrons. No, always keep in mind which group it's from. So this is in group 3, only has 3 electrons in its outermost shell. 1, 2, 3, gone, dusted, finished. So you're not going to show any lone pair electrons just to complete the octet rule. Again, group 2, 2 electrons involved in bonding. You're not going to make any electrons from your own just to complete the octet rule. It is what it is. Yeah. Now there's another problem. That's called the exceeding the octet rule. Defying and exceeding. This is also defying. Is this the spelling of exceeding? Exceeding the octet rule? Okay, I'm not an English teacher. You can fix the exceeding spelling of exceeding. Exceeding the octet rule. And that's normally period 3. They're like, hey, some of you have fewer electrons in your outermost shell, which, you're not exceeding the octet rule, but you're not actually also adhering to the octet rule. You have 6 electrons, not 8. So you have fewer electrons than the octet. But sometimes you can have more electrons than the octet, right? And that's usually period 3. Why it's usually period 3? Nobody tells you this, but I'll tell you in a while. But for now, understand it's like, mainly it has to do with phosphorus, it has to do with sulfur. These are the 2 culprits mostly that are also a part of your course, which you need to know defy the octet rule in certain cases, right? And why does it defy the octet rule? For that, I want you guys to write the electronic configuration of phosphorus, write the electronic configuration of sulfur. And before writing the electronic configuration, how many principal quantum numbers are there in phosphorus and sulfur? How many principal quantum numbers are there? You have principal quantum number 1, 2, and 3. It's in period 3, right? Has 3 shells. So PQN 1, 2, 3. This has PQN 1, 2, 3. And if it has 3 principal quantum number, the first principal quantum number has the 1s subshell. The second principal quantum number has the 2s and the 2p. The third principal quantum number has the 3s, the 3p, and the 3d. True? Similarly here, the first principal quantum number has the 1s subshell. This has the 2s and the 2p subshell. And again, in the subshell, in the p subshell, there are 3p orbitals. In the d subshell, there are 5d orbitals. I don't care about the orbitals, just the subshells for now. And then the 3p has the 3 principal quantum number has the 3s, the 3p, and the 3d. Agreed? Agreed. We all are in agreement to it, right? And how many electrons can principal quantum number 3 hold? Just if I look at the max number of electrons that this PQN can hold, I can find this 2 times 3 square. That's 18. And you could have even said, hey, D holds max of 10. How 10? Because it has 5 orbitals, each orbital max of 2. So 10 here, 6 here, 2 here, 18. 10, 6, 2, or you could use 2n square. Yeah, that's how many electrons the principal quantum number 3 is going to have. We've already done this in chapter number 1, right? But I'm recapping this for a particular purpose. And that purpose you'll understand in a while. But for now, I just want you to make certain structures. For now, this I've written, this is the why. I'll tell you the why in a while. But for now, your exam requires you just to make these structures. So can we make these structures? Like SO2, like SO3. These are proven structures. They've proven it. You don't need to prove them. The examiner will give you the formula. He'll say, make the dot and cross diagram for this fella. Make the dot and cross diagram for this fella. And you just have to use your brain. Don't forcefully complete the octet. If it's going above the octet, let it go. If it's going below the octet, let it go, right? So if you look at SO2, it's S being bonded to O and being bonded to O, double bonded. If you look at SO3, it's S double bonded to one O, double bonded to the other O, and double bonded to the other O. These are proven structures. PCl5, if you look at PCl5, it's phosphorus being bonded to 5 chlorine atoms. And since phosphorus is in group 5, one bond will go here, one would go here, one would go here, one would go here, one would go here. That's proven. Sulfur, group 6, all the 6 electrons are utilized. You know, that can happen. This can literally happen. Appreciate it. Oh my God, beauty of chemistry. Beauty. This can happen, absolutely. And now you just need to make the dot and cross. You just need to make the dot and cross. Please make the dot and cross, and then I'll explain why they defy it. I'll explain why they defy it. Just make the dot and cross for now. Let's make it. Do you want me to make it with you, or can you make it on your own? Just realize that each stick represents a pair of electrons, and always know which group it's in. So if sulfur is my central atom, always know it's in group 6. And obviously oxygen is also in group 6. So just to make sure that you are writing the correct number of electrons. This was in group 5. This is in group 6. This will help you identify the number of electrons. So SO2 has 10 electrons. Yes, Fatma, you are right. You are absolutely right, Reno. That's what I want to develop. I want to develop the idea that it's possible. Appreciate it. It's possible. You can defy the octet. You can defy the octet. Either you will have fewer electrons than the octet, that's usually period 2, or you could have more, you could exceed the octet, that's usually period 3. And in particular, it's phosphorus and sulfur. And I'll tell you why. I'll tell you the why in a while. Abhi batata hu na, pehle ye draw to kare. First draw it and then I'll tell you the why. Okay, go on. Now, I've given you guys your 5 minutes. Let's see if you have drawn it correctly. Now, sulfur, let's make SO2 first. Let's make SO2 first. So S bonded to O, bonded to O. Proven structure. S bonded to O, bonded to O. Okay, that's pathetic circles by Sir Suleiman, but hey, who gives a crap? That's O, that's O. Now, each bond represents a pair of electron. So, a pair of electron and a pair of electron. A pair of electron and a pair of electron. Good stuff. Happy, happy. Now, oxygen, group 6. See, after you do the bonding electrons, always look at the lone pair electrons. You have to identify lone pair. So, oxygen group 6 contributed 1 electron to this bond, 1 electron to this bond. How many are left? 4. So, it's 2, 4. That's 2, 4. And sulfur, give 1 here, 1 here, 1 here, 1 here. Group 6, 2 are left. That's 2. Happy? Good stuff. Sir, mine is correct. Sir, I have also done it correct. I can't believe I've done it correct. Believe in yourself. I believe I can fly. I believe I can touch the sky. It's pretty easy. It's like puzzle. It's like a puzzle. Okay. S over 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 over. I'm gonna get 0 marks on these diagrams, to be honest. You know, look at this. This is pathetic. Look at this place, this place, this place. So it's better even if you don't draw the circles. It's better, but it doesn't really make a difference. Make a difference. So each bond represents, each stick represents a pair of electron, pair of electron, pair of electron, pair of electron. So again, pair of electron, 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 pair of electron. Good stuff. Sulfur, group 6. So it had 6 electrons. 1 was given to this bond, 1 was given to this bond, 1 here, 1 here, 1 here, 1 here. Boom shakalaka, it's done and dusted. It gave all of its 6 electrons. What about oxygen? Group 6 had give 1 here and 1 here. 4 are left. So 2, 4, and 2, and 4, and oh, that's pathetic. That's 2, and 4, and 2, and 4, and 2, and 4. And now notice something. Exceeding the octet. 4, 8, 12. That's a voice crack. So, what are you doing? Look at this sulfur. 2, 4, 6, 8, 10. That's beautiful. Appreciate it. Happens. PCl5. You know, P bonded to 5 chlorines. Okay, it's like a Medusa witch. SP1. Oh my God. 1, 2, 3, 4, 5. So Cl, 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 Cl. Good stuff. Now phosphorus. Now each bond represents a pair of electron, pair, pair, pair. So it's like a pair, like a pair, like a pair, like a pair, like a pair. Done. And phosphorus was in group 5. So always write this. Phosphorus group 5, give 1 here, 1 here, 1 here, 1 here, 1 here. Done and dusted. No more electrons left. Chlorine group 7, give 1 to the bond. 6 are left. 2, 4, 6. 2, 4, 6. Outermost. 2, 4, 6. These are lone pair electrons. 2, 4, 6, whatever. 2, 4, 6. Done and dusted, done and dusted. Easy peasy lemon squeezy, guys. Literally, that's all there's going to be asked in the exam. All that's going to be asked in the exam. And you guys think A-level is difficult? What's difficult? SF6. Do that stuff. Let's just do this. Party wala dance. 1, 2, 3, 4, 5, 6. Okay, pathetic drawing, Suleiman. 5, 6. It's like an easy mark. So SF6, and if you look at the structure, it's like S bonded to 6 Fs. S F F F F. मेरी एक दोस्त होती थी ना, उसको मैं पढ़ाता था, तो I used to teach her, and she was like, नहीं ना समझ आ रहे, नहीं ना. I hope nothing like this is happening, I used to teach, and then she used to use Instagram. तो मैं क्या करता? And she was नहीं ना समझ आ रही, नहीं. So I hope nobody's using Instagram. Okay, SF6. Each tick represents a pair of electrons. So pair. How easy is this? It's so easy that it gets boring. It gets me bored. So easy. And then sulfur was in group 6. Utilized all its 6 electrons. 1, 2, 3, 4, 5, 6. Why have I drawn 7, Suleiman? You dumbo. 6. Yeah. And then for fluorine, group 7. So 1 is involved. 3 are left. 3 pairs left. 3 pairs left. You guys like this structure? Yes, sir. Any questions for now? Why does this happen? I'll tell you the why. Oh, this is a beautiful question. I love this. Student is saying, sir, but fluorine and sulfur, they also have inner shells. So wouldn't they be counted as lone pair electrons? Absolutely not. Absolutely not, because the definition of lone pair electrons are, listen to it carefully, the outermost electrons which are not involved in bonding, not the inner shell electrons. So these are the lone pair electrons. Yes, there may be 2 electrons in the inner shells, but they are not lone pairs. These are called lone pairs, the ones which are in the valence shell but not involved in bonding. Right? Now, why, sir? Why is one having fewer? Why are these the structures? The examiner will give you this. They'll just expect you to draw it, but you need to know the why. Why period 2 has fewer electrons than the octet? Why period 3s have, not all of them, but why some of the period 3 elements have more electrons than the octet? I've given you guys an initial idea here just to, spice it up for you. I made you guys recall this. But before I further go into this, I want to talk about a little concept called hybridization. Once you understand hybridization, and obviously this is the half-cooked concept. So this is not the complete idea of hybridization, but a half-cooked concept. You learn more about this in the upcoming classes. But initially, I just want to talk a little about hybridization, right? Now, what we understood previously was that for orbitals to overlap and bond, normally it must be singly filled. Right? Here comes another curveball. So normally, for example, I talk about F being bonded to F. What's the electronic configuration of it? It's 1s2, 2s2, 2p5, right? And if you look at 2p5, it's basically the 2p subshell. And if I look at the orbitals, it's 1, 2, 3, and 4, and 5, right? And the reason why fluorine bonds with another fluorine is because it has a singly filled orbital, they overlap, and that's called the head-on overlap. Sigma bond forms, and that's the FNF bond right here, right? So normally when orbitals overlap and bonds form, the orbitals must be singly filled, right? Singly filled. And we've learned that in for our oxygen, for our fluorine, for our chlorine, and so on. But let's look at the exception. BeF2. Why is the BeF2 structure possible? We wrote the structure like so, or BeCl2 or BeF2, whatever, it doesn't really make a difference. This is also an exception. If you draw BeF2, this will be the exception right here. If you draw BeF2, it will look the same as BeCl2. But why? Why is this the structure for it? Why is this bond going to form? Why is this bond going to form? The idea should be, your brain should go into the idea of orbital overlap. And you guys should think to yourself that, sir, orbital overlap is going to take place. I'll say, okay, orbital overlap takes place. Why? And you guys would tell me, sir, because they singly filled they're singly filled orbitals and then they're gonna overlap. Okay, that's a sigma bond, that's a sigma bond. Single bonds, always sigma bonds. Okay, I'll agree with you. If that's what's going on in your brain, and that should be going on in your brains, I'll agree with you. I'll agree that, okay, there must be orbital overlap for these bonds to form. Done. They both must be sigma, because single bond sigma, single bond sigma. Only a double bond has a sigma and a pi. Triple bond sigma and two pi's, right? So singly filled. And the reason why this overlap would take place is because the orbitals must be singly filled. Agreed. Everybody agrees with me. Everybody agrees with me. Now write down the electronic configuration. Write the EF, write the electronic configuration. And not the subshell electronic configuration, I want you guys to write the orbital electronic configuration. So for fluorine, I'll write 1s2, 2s2, 2p5, that's the subshell electronic configuration. But I want to write the orbital, the p orbital, yeah, or you could write the s and the p both. It doesn't really make a difference. 1s, 2s, and let's write the orbital electronic configuration. So that's the 1s orbital, the 2s orbital, and the 2px, the 2py, the 2pz orbital. X, Y, Z. That's it. So that's okay. Singly filled, sir. And so if this is singly filled, sir, you are so awesome that this is singly filled, and 2p, this will also be singly filled, I shouldn't be drawing it like this, but okay. This is also singly filled, singly filled, singly filled. So they are going to overlap with the singly filled orbital of beryllium, right? Everybody is saying this. Agree with me, please. Agree with me that these two singly filled orbitals are going to be overlapping with beryllium singly filled orbitals. Please write down the electronic configuration of beryllium. Beryllium has, write down the electronic, it has 4 electrons. So you could even write it on your own. Instead of looking at the periodic table, 4 electrons is what? 1s2 and 2s2. Yeah? 1s2 and 2s2. So if you look at the electronic configuration for it, prank ho gaya. If you look at the electronic configuration, how in the hell is it going to undergo chemical bonding? How in the hell is beryllium undergoing chemical bonding? It doesn't have a singly filled orbital, does it? Does beryllium have a singly filled orbital? No, it doesn't. How in the world is it bonding with fluorine atoms? How in the world? That idea is called hybridization. So what happens is, you need to look at the principal quantum number as well. What's the principal quantum number? Principal quantum number 2. And what I asked you above was that in principal quantum number 2, how many subshells are there? How many subshells are there in principal quantum number 2? You have the S subshell, the 2s subshell, and the 2p subshell, yes? So the 2p subshell exists. The 2p subshell exists, but it has 0 electrons in it, because it's principal quantum number 2. So principal quantum number 2 has the S and the P, but we write 1s2, 2s2 because the P subshell does not have any electrons. Even if you wrote the electronic configuration like this, you would have gotten the marks. But the P subshell does exist, but in some books you'll see it like this even. It does exist, but it has 0 electrons, right? So the P orbitals would exist and have 0 electrons. Now what happens? This beryllium cannot undergo chemical bonding because it's fully filled. It's not singly filled. You need singly filled orbitals to undergo chemical bonding. So what happens is, one of these electrons gets excited because realize that bond formation is a favorable process. So just to form bond, this guy gets excited and goes here. Because the energy that it needs to get excited from this to this is way less than the energy released when these bonds form. So it's actually favorable. It's favorable for it. It'll say, hey, even if I need energy to jump from point A to point B, I will do that because once I bond here, I'll release much more energy and I'll be much more stable. So what it does is it jumps. And once it jumps, that's how the electronic, so now it's the excited state. Remember when the idea about the excited state, the one we learned in electronic configuration, chapter number 1. So this is what happens. Now they're ready. Now it's ready. So one is gonna bond right here, sigma, and the other bonds right here, sigma. That's what happened. And this idea of jumping from this orbital to this orbital, that idea you could say is roughly called hybridization. Roughly. It's not true, but roughly for now you could say that's hybridization. Because hybrid, B-R-I-D, hybridization. Because in reality what happens is, once you have the 2s, I'll tell you what hybridization is, after a couple of classes in a lot more detail. But for now, just understand that when the electron goes here, it doesn't really jump. What happens is the 2s orbital mixes with the 2p orbital, one of the 2p orbital, right? So the 2s orbital mixes with one of the p orbital, right? So one s orbital and one p orbital mixes together to give you a hybrid orbital. The hybrid orbital has more energy than the s orbital but less energy than the p orbital. If this is the s orbital and that's the p orbital, here is where the hybrid orbital lies, you know. So what happens energy wise? So what happens is that once this jumps here, it's not actually a jump, it's a mixture of these two orbitals. Both the s orbital and the p orbital mixes to give you two new orbitals, and that's called, because one s orbital is mixing and one p orbital is missing. A p orbital and an s orbital is mixing. That's why it's called sp hybridized. And you learn more about hybridization later on, but this is just an initial idea into hybridization. So just for the purpose of bond formation, they're going to get excited. They're going to be like, ooh, let's go, let's play football, let's go, let's bond, you know. So just for the purpose of bond formation, you know, although if you look at it, it is not going to hybrid, it's not going to undergo chemical bonding, it's just fully filled. But you realize it's principal quantum number 2. It also has the p orbital. It's empty, but it is there. It's there. So what happens is a mixing of these orbitals takes place. And because an s orbital is mixing with a p orbital with one p orbital, that's why it's called 1p sp hybridized orbital, or sp hybridization. And that's how BeF2 forms, right? And that's how it does not have a complete octet. Look at these two empty guys. Look at these two empty fellas. That's why it's not hybridized. That's why it's not the octet is not complete. Yeah. That's why. That's the reality. That's literally the reality. How did we see this? We saw this through X-ray photographs and X-ray diffraction and blue blah blue. That will show you the shape and whatnot. X-ray diffraction and what. You could search more about that later on. Hybridization in its entirety is a little different, but for now, I just want you guys to understand the initial idea is that just for the purpose of bonding, the s and p orbital, one of the s orbital will mix with the p orbital to have two singly filled orbitals in order to make these two bonds. So you need two singly filled orbitals in order to make these bonds. So if not singly filled, it goes here. Hybridization takes place. Mixing of 2s and 2p takes place. And therefore you get a 2sp hybridized orbital. It's a 2s and a 2p, so it's a 2sp hybridized orbital. Yeah? Pretty fun, huh? Pretty fun. How about BF3? Can you guys do BF3 on your own? Can you guys deduce the logic behind BF3 on your own? So if you want just to talk about the F stuff, you know, I'm just going to draw the F orbital, the fluorine atoms orbitals. So it's 1, 1, 1, 2p5, right? So 2p5. That's the other fluorine atom. Can you guys draw it on your own? I'd love to see you guys try. You know, that's what scientists should be doing. I'd love to see you guys try. You know, that's poop, poop, and poop, and poop. So these are singly filled. Can you write the electronic configuration of boron, please? Can you write the electronic configuration of boron? Sir, is there any other element in which hybridization occurs? In roughly roughly hybridization occurs in all elements when they undergo chemical bond. Roughly, not in all, but like in most, roughly. And you'll see that throughout your chemistry. Even in organic chemistry, you'll see a lot of hybridization. Just for the sake of bonding. Because realize the idea behind bonding is not just to have a complete octet. It's to be stable energetically, to be stable. It's to be energetically stable. But yes, if the examiner were to ask you, why are noble gases stable? Don't say they are energetically stable. No, stay there stable because they have a stable electronic configuration. That's it. Finished. So the O-level logics still apply. It's just these exceptions that you need to understand. Can you guys do it for BF3? Please. Can you write the electronic configuration of boron? Boron has 5 electrons if I'm not wrong. It is proton number 5, so 5 electrons. So it's 1s2, 2s2, and then 2p1. Yeah? I'm just drawing the orbital electronic configuration. How in the hell can it make 5 bonds, sir? It just have one singly filled orbital. Oh my god, how in the world can it form 5? Do it. Think. I'd love for you guys to think and, you know, come up with a solution for this. How will it make 3 bonds? That's what I want to do. I want you guys to think. See, chemistry is pretty easy, huh? I also want you guys to do CH4 on your own. Just to explain hybridization to you a little. Teachers butcher the concept of hybridization. They butcher it. They literally butcher it. Okay, let's see what Fatma has to say. The electron from the 1s and 2s get excited to form a hybrid. Fatma, you are partially right. Partially right. But realize it's not from the 1s. It's just the 2s says, hey, this can already make one bond. You just need two more singly filled orbitals. So if this electron, the 2s electron, if this were to jump to the p, what's going to happen? What's going to happen? You automatically have, Fatma, you automatically have three singly filled orbitals. Three singly filled orbitals. Singly filled, song a single lady, song a single lady, na 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 na. And then this would bond here, this would bond here, and that would make the third bond. Sigma, sigma, sigma. That's all. That's literally all. That's it. And what would I call this? How many orbitals have mixed? It's the 2s orbital, one of the 2s orbital, and one 2px and one 2py. So there are two p orbitals which have mixed, and there's a single s orbital which has mixed, and there are two p orbitals which have mixed. So because one s has mixed with two p's, you call this the sp2 hybridized orbital. Just for the sake of bonding, this hybridization took place. And it's 2sp2 because it's the two principal quantum numbers. So it's the 2sp2 hybridized orbital. So this is just mixing. And you learn more mixing later on. I also want you to write CH4 on your own. Do CH4 on your own. Or CF4, whatever you like. CH4, CF4. H4 is easier. It's just 1s. Hydrogen is just 1s. I'll write hydrogen for you. I write the subshell electron. That's why if you've not watched the previous recordings, you aren't getting jack shit. Because everything is connected to electronic configuration. Electrons are the backbone of chemistry. Carbon. How many electrons? And see, that's the reason why it does not follow the octet rule. Look at this beauty. This is still empty. This is still empty. In boron's case, in beryllium's case, two orbitals are empty. See, it's 4 deficient. Once it makes this bond and this bond, this will be complete. So this will be double, but there'll be 2 empty orbitals. So it will be off the octet rule by 4 electrons, and you'll see it here. See, just connect things. Beryllium, if you look at where is beryllium, where is that beauty? Where is that beauty? Beryllium. See, it's off by how many electrons? 4 electrons. And if you look at boron, it just has 1 empty orbital then. So it's off by 2 electrons. See? From the octet rule. Song a single lady, song a single lady. Na 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 na. I'm loving this. I love it when I teach so good. Okay, are you guys actually getting it or not? Are you guys actually getting it? Enjoying it? More than getting it, I want you guys to be enjoying it even. Are you guys enjoying it? Safa, are you enjoying this? Where's Safa? Safa, are you enjoying this? Yeah? Yes, Yusuf is saying, yes sir! Yusuf न थे मगर सरे बाजार आ गए खुश फहमियाँ ये थी कि खरीदार आ गए आवाज़ दे के छुप गई हर बार जिंदगी हम ऐसे सादे दिल थे कि हर बार आ गए wow. So it has 6 protons, therefore 6 electrons, carbon. Can somebody write its electronic configuration? The subshell, it's 1s2, 2s2, that's 4, and 2p2, right? That's 6. And you could use the periodic table. So 1s2, 2s2, and 2p1, 2p2. How in the helly? What the helly? How is it making 4 bonds with hydrogen? Or maybe 4 bonds with fluorine? Then in case of fluorine, it would be 2p5, the one that we've done above. Let's use hydrogen for now. How would this happen? You need 4 singly filled orbitals. But what's happening? You have 1, 2, and only 2. So only 2 bonds should take place. Why are 4 bonds taking place? Think. The concept of hybridization. Shaba. Yeah? Yes, sir. Yes, you are right, Fatma. Fatma thinks that the 2s should get excited. The 2s should get excited, go from here to here, mixing of these beautiful orbitals. These beautiful orbitals. So this should be, 1s2, 2s1, and 2p. Uno, dos, tres. And this would make a bond here. This would make a bond here. I'm all about the bond, and chicken. Yeah. 4 bonds. Happy? What would I call this? What would be the hybridization of this? Teachers will make you rote learn the hybridization. This is sp2, this is sp3, this is sp. What do you think this would be? See, the notation of hybridization comes from how many orbitals are involved and which orbitals are involved. See, you have an s orbital being involved and 3p orbitals. So what should you call this hybridization? Should I call this the 2sp hybridized, the 2sp2 hybridized, or the 2sp3 hybridized? Is it sp3 hybridized, sp2 hybridized, or sp hybridized? sp2, sp3. Think, Fatma, think. See, how many orbitals were involved? Let's go back. See, here it was an s orbital being involved with the p orbital. So it was sp hybridized. In this case, there was the s orbital and there were 2p orbitals involved. So it was sp2, 2 p's and 1 s. Yeah, and I put a 2 because that's the principal quantum number. So now think, this is the S and 1p, 2p, 3p. Yes, sir. So it is the sp3 hybridized orbital. And you will come across this so many times in hybridized in organic chemistry. This is sp3 hybridized. And you could add the 2 here, but nobody cares. 2 is just the principal quantum number. Awesome, guys. Awesome. Let's look at and see. In this case, it will not defy the octet rule, because see, once it bonds, they'll be paired, happy, not defy. And CH4 does in fact not defy the octet rule. So it'll only defy the octet rule if you have, like, see, you have empty orbitals here. Yeah, that is fewer electrons than the octet. But when we talk about exceeding the octet rule, why does that happen? Now let's look at the why. Remember I said it's normally period 3 and it's like phosphorus and sulfur, and your brain is about to open. So if you talk about SO or if I talk about SF6, I'll just give you one idea. I'll just talk about SF6 to give you the idea. That's it, because I'm short on time. SF6, that's it. That's the last idea that I'm going to give you, and then you're good to go. Now, SF6, right? F, the outermost orbitals for F is 2p1, 2p2, 2p3, and that's it. 2p5, right? That's the subshell. So I'm just drawing the orbital electronic configuration. 1, 2, 3, 1, 2, 3, praise, mrace. And you could duplicate that 6 times. You could duplicate this 6 times. Yeah, I don't really care. Can somebody write the electronic configuration of sulfur? What is sulfur's electronic configuration? Also check out which period sulfur is in. Which period is sulfur in? Which period, guys, is sulfur in? Which period is sulfur in? From the periodic table, can you guys check which period sulfur is in? I'll show it to you. Because you won't do it on your own, so I'll have to show it to you. Sulfur is in period 3, which means it has 3 principal quantum numbers, right? It has principal quantum number 1, 2, 3. Can somebody write the electronic configuration of sulfur? What is it? It's 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4. True? So we'll write it. How many electrons does sulfur have? It has 16 electrons. Yeah, let's go. 16 electrons. And I could even write it without looking at the periodic. But I know it's in period 3. That's important for me to understand the why. So period 3 means it has 3 shells, 3 principal quantum numbers. Principal quantum number 1, 2, 3. Right? And let's first write the electronic configuration. It's 1s2, 2s2, 2p6, 3s2, and 3p, how much? 16 in total. So 4, 10, 12, and 4 more. Yes? Agreed. Everybody agrees. Awesome. Now, please understand that if it is in, let's also write the subshell electronic configuration first. Yeah? So it's 1s2, the orbital electronic configuration is 2p6, and then it's 3s2, and then it's 3p4. 2, 3, 4. So 1s orbital, 2s orbital, 2p orbitals, because a subshell is basically a combination of a single orbital, or a subshell is either a single orbital, the s subshell is the s orbital, the p subshell is a combination of these 3p orbitals, right? Studied this in chapter 1 when we were chunu munu. That's the electronic configuration of sulfur, right? If you look at principal quantum number 3, if you look at period 3, it means it has 3 shells: principal quantum number 1, principal quantum number 2, principal quantum number 3. Principal quantum number 1 has only one s subshell. Principal quantum number 2 has a 2s and a 2p. Principal quantum number 3 has 3s, 3p, and it has 3d, everybody. Yes, it does in fact have 3d, but the 3d orbitals are 0. It has no electron. Because see, principal quantum number 3 means you would have s, p, and d. But the reason why we don't write d is because there are no electrons in d. Some books would also write the electronic configuration of sulfur as 1s2, 2s2, 2p6, 3s2, 3p4, and 3d0. And that's also correct. That's absolutely correct. You could also write this in the exam. He will give you full marks. It's better to write it like this, but you could also write it like this. They'll give you full marks for it. No worries. No problem, Arino. That's fine. The 3d does exist because it's PQN3. PQN3 has SPD. It does exist, but it's 0, right? So if I'm able to move this, oh no, I can't. What the hell-y? What the hell-y? Let me just erase this stuff and write the 3D subshells, 3D orbitals for you. So 3D has 5 orbitals, and that's empty. That's empty. Now the question is, how in the world can sulfur form 6 bonds? 6 bonds. It should usulan, by law, by book, it should only form 2 bonds. It should only form 2 bonds because you have 2 singly filled orbitals. 2 singly filled orbitals, right? So it should only be SF2. Why is it SF6? Again, the idea of hybridization. There must be 6 singly filled orbitals now. 2 are already there. So if 1 goes here, that will make 4 singly filled orbitals. Why 4? Because if 1 goes here, then this is singly filled, this, 4 singly. Then you don't need 4, you need 6. Then this fella also goes here. So it's a mixture of SPD, but that's not in your course. I don't need to call this hybridization whatever, but it's the 3s and the 3p would get excited just for the sake of bond formation, and it would look something like this. So it's 3s1, 3p1, 2, 3, because this fella went here and this fella went here, right? So now they're singly filled. And this is the D and that's the D. And so now this will bond with the fluorine atom sigma, 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 and sigma. All 6 bonds right here in front of you. And that's why it exceeds the octet rule. Why does it exceed the octet rule? Because it has a d orbital as well, but that's empty. So the electrons can get excited and move on to the d orbital. And fun fact, guys, why doesn't this happen? You guys might think, sir, should it not have happened for beryllium or boron? Why didn't it happen for beryllium and boron? Because they were in period 2. Now you understand why I say period 2. Period 2 because they did not have the D subshell. Period 2 has only 2s and 2p. It does not have the D subshell. So if it does not have the D subshell, how in the world are you expecting them to go into the D orbital when the D orbital does not even exist in period 2? That's why period 2s, they don't expand their octets. They don't expand their octet. They don't defy the octet rule by exceeding the octet. They have fewer electrons than the octet. See these beautiful empty orbitals? But the ones which are in period 3, normally, like phosphorus and sulfur, why do they defy the octet rule? Why do they exceed the octet rule? Why? Why do they exceed? Because they have a d orbital to go to. They have a d friend. They're like, hey D, can we go to you just for the sake of bonding? Because we like bonding, we like bond formation. Bond formation is favorable process. Can we do that? And D says, okay, fine, sure, come on, let's do this bonding together. So they do it. One more thing. Remember when I roughly talked about the idea of why this beryllium boron, why don't they just take electrons from the outside? Why not just for the sake of it? Why not just for the sake of it? Just for the sake of completing the octet, why don't they just take electrons from the outside? Why not? Why not? Because they're not that electronegative. If you forcefully give them electrons, you could do that, but then that would make them extremely negatively charged. The negative charge would be concentrated, and that would make them unstable, and no atom wants that. So it's going to be unstable. It'll go back to its own position. So it's not that electronegative. But sir, phosphorus and sulfur, everybody, phosphorus and sulfur, can they also take electrons from the outside? Can phosphorus and sulfur take? So this idea also applies to phosphorus, the same idea. Because it's not in your course, I'm not going to go into it. I just gave it in, a lot more detail than is required. But phosphorus and sulfur, are they not towards the right of the periodic table? They are. They are towards the right of this periodic table, right? They are. So are they not electronegative? They are. And if they are electronegative, that is the reason why these polyatomic ions are formed in O levels and IGCSE. You say PO4 3 minus, you see SO4 2 minus. Remember the structure of PO4 and SO4 when I taught you O levels and IGCSE? I said, hey, you don't need to know this, but SO4 looks something like this. It's sulfur being bonded to 3 oxygen atoms, 6 bonds are complete, and then this is 1 O, and this O, there's an electron coming from the outside. There's an electron coming from the outside. Why? Because of the entire idea of electronegativity. That's crazy. That's beautiful. So you need to understand that just because they're electronegative even, they'll exceed the octet because they have a d orbital. The examiner has never asked this, but please understand that the examiner can ask this. This is not directly in your course, but A-level students should be tippy-toppy with their concepts. So the d orbital, because there's the presence of d orbital, that's why they can exceed the octet rule. Why doesn't period 2s exceed the octet rule? Because there's no d orbital in the period 2. Where would they go? Where would the electrons go? There's just 2s and 2p. They can only play around with s and p. Yeah, so that's the idea of exceeding the octet rule. Is that in your course? No, it's not. This entire explanation is not in your course. Never been asked, but, like I said. Any questions up until now? Okay, Manur has asked a question, sir. If all of these bonds are sigmas, when will a pi bond form? Manur, a pi bond is a double bond. I hope you've taken the last classes. All the single bonds are sigma bonds. F single bond, F single bond, F single. These are all single bonds because the first bond that forms is a head-on overlap. So it's a head-on overlap, head-on overlap, head-on overlap, head-on overlaps, right? But if you have a double bond, Manur, then the first bond, we know a single bond, the first bond is always going to be a sigma bond. But in a double bond, the second bond now will be the pi bond. Because now, once the head-on overlap has taken place, in a single bond, the head-on overlap took place. Now, what about the second bond that's forming? That's forming through the sideways overlap. Here, it's just single overlap, head-on overlap, head-on overlap, head-on. There's no sideways because there's no double or triple bond. Pi bond only exists in the idea of double bonds and triple bonds, Manur. Make sense? Any questions, guys? Any questions? Yes, sirree. Any questions? We are left with, there are a total of 14 lectures of chemical bonding. We are done with 5 lectures, 9 more lectures to go. And then we'll officially be done with chemical bonding. That's the lengthiest, the lengthiest. I'm taking my sweet time on it. Manu is saying, yes, got it. Thank you. Any questions, guys? If there are any questions, you are free to ask. You are free people. So, Zumar has asked one of the most beautiful questions asked ever. And Zumar, you have 500 rupees inam from my side. You can ask me about, you can send your EasyPass account and I'll send it. Zumar has said, sir, in chapter number 1, we said that the 4s is filled before the 3d as it has a lower energy level. We agree. Now, Zumar is saying, so why doesn't the electron go to the 4s instead of the 3d? Because there is no 4s here, Zumar. It's in period 3, Zumar. Period 3 means 3 shells, and 3 shells mean principal quantum number 1, 2 and only 3. There's no principal quantum number 4, because if there were principal quantum number 4, it would have been in the period 4, but this is period 3. Period 3, 3 shells. So there is no principal quantum number 4. What else do I have? What else option am I left with? 3D does exist here. 4s doesn't even exist because it's not in period 4, Zumar. Oh, beautiful question. Beautiful question. Yeah, Zumar, I love it. Love it. Yeah, that's why I wanted this to come in the recording. Got it, Zumar? You see, period 3 mein, na? Yes, sir. Yeah, such a beautiful question. Such a beautiful, like, see, if Zumar, it was somewhere here, then you would go into the 4S and then the 3D, but it's here. These fellas are right here.